Hi guys. Okay, so today is our Unit 2 review. Do either one of you have any questions about any of the lessons in Unit 2?
I have a question, but it's not about the lesson.
Okay,
So I just realized that the midterm exam is on Friday,
yeah.
and I have school like till 3. So I don't know. Yeah.
Okay. All right. So I have some flexibility. I can adjust the time and we can do it after you get home from school. How about you, Sasan? Do you have any limitations on Friday of the midterm?
Friday, let me check for a second.
So Judy, what time do you think you will be home and ready to begin writing the midterm?
5 would be good.
What time, sorry?
5?
5-ish? Okay, 5.
Yeah.
All right.
So I guess I have class till till 6, from 4 to 6.
From 4 till 6. Okay. So and at 6, are you then home or are you out?
I'm home.
You're home. Okay, so if we schedule the midterm for 6 or 6:30, 6:30 until 8:30, is that okay with both of you?
That's okay.
Yeah, that works for me.
That works for you? Okay. So I'm gonna let the office know, the school know, we're gonna adjust the time. And so yeah, thank you for bringing that to our attention early on so that we can change our schedule and plan for that. Okay, so right. Now, any other questions? Any questions about the lessons? I can just go through the slides one by one and we can think about it. We can talk about it. So we started this unit is about organic chemistry. Our first lesson of the unit, lesson 5, was about the hydrocarbons. And we talked a little bit about saturated hydrocarbons and unsaturated hydrocarbons. We talked about the idea of structural isomers. We reviewed naming of hydrocarbons, naming of alkanes. Has anybody been working on the practice questions? And by practice questions, I mean the support questions like this one. Has anybody been trying these?
I think I've done some, but like I don't have them right now.
Okay. So yeah, I really advise you guys to be practicing with these. And if you think you don't know how to do some of them, really these review sessions are a good time to take up those kinds of questions. In previous times that I've been teaching this course, this is the time where students come to me and say, for example, I tried, naming this compound, but I wasn't really sure, or I ran into some problems trying to name this one. How do you name this one? And we go through it and we talk about it. I really hope that you guys could do the same and we can talk about these things. But maybe what we can do is actually we can take up that periodic table diagnostic that I sent out to you guys to do a while back. So let me just share that screen with you. Okay, so everybody see the periodic table worksheet?
Yes.
Yeah, okay, good. So let's talk about a little bit about, so what are some of the answers here? So, and I would really like both of you, since you guys are the only students here today, think about it as you're getting a semi-private lesson here today, so which is great. So feel free, just jump in with answers and don't worry about if you have it wrong. It doesn't matter. We are here to just figure things out and learn. If you guys knew all the answers, you wouldn't be registered in this course. So how about periodic means? What does periodic mean to you guys? Judy or Sasan, one of you want to take a chance with this? How about we alternate? Judy can answer, the next one Sasan can answer, and we'll go from there. And if the answer is right, great. And if the answer is wrong, I'll tell you the right answer. Okay, so periodic means. What does periodic mean? The periodic table. What's periodic about it? What does periodic mean?
Like occurring or
yeah, go on.
reoccurring, yep. Like at the regular intervals occurring.
Yeah, exactly. It's recurring at regular intervals. That's exactly what it means. Yeah. So that's exactly what it means. So yeah, that's exactly what this is. This is recurring at regular intervals. And I just noticed that I am showing you the answers. Okay, so what about a group or a family? What is a group or a family? What do we mean by
like they have the same I can't even say it. Like the same electrovalence, for example.
the same, sorry?
Same I can't say it, so I don't know how.
Yeah, same characteristic.
Yeah,
characteristic.
like depending on their family. Yeah.
Yeah. Okay. So that's exactly me. When you group something together or you put them in the same family, it means they share certain traits. They have certain things, certain properties, certain characteristics in common. And for us, relating to the periodic table, the groups or the families are those vertical columns on the periodic table. So the first column, the first group, the second group. So all the elements that fall into that column, that vertical column, have got the same type of property. They belong to the same family. If you look at the very last column of the periodic table, and let me just see if I can quickly throw up a periodic table here on the screen. And okay, so just going to change the share with you to show you the periodic table. Okay, so everybody can see the periodic table?
Yes.
Okay, great. So the groups or the families actually here on this periodic table, they're labeled. So the groups are these columns here. So this is group 1, group 2, group 3, and so on, all the way to the end. So the elements that are all lined up under this group 1 share certain things in common. The elements under this column share things in common. The elements, for example, in this very last column share certain properties in common. So that's what we mean when we talk about groups. Now, how about periods then? What are periods?
Just rows in periodic table.
Yeah, exactly. Those are the rows in the periodic table. Exactly. So again, the rows across on the periodic table. And then the groups, if you remember, they are the ones that tell you how many valence electrons are available. So for example, hydrogen has got 1 valence electron, or lithium has got 3 valence, not 3 valence electrons. Lithium also has 1 valence electron because they all belong in group number 1. Sodium has got only 1 valence electron. They belong in group 1. For example, oxygen has got 6 valence electrons. So does sulfur. Carbon has got 4 valence electrons. So these numbers, the 13, 14, 15, 16, 17, 18, they are also oftentimes written as 3, 4, 5, 6, and these are also written as 3A, B, C, 3A, 3B, 4A, 4B. So really, we are mostly talking about 1, 2, and then 3, 4, 5, 6, 7, 8. So carbon belongs to group 4, has got 4 valence electrons. Nitrogen belongs to group 5, has got 5 valence electrons. What else? What's the next question? The next question is, how can you determine the number of electrons in an element's outer energy level by the group that it's in? And this answer we were actually just talking about right now. So anybody want to put it into their own words and say it for me?
So like just looking at the group numbers, those numbers gonna be the electrons?
Mm-hmm. Yeah, exactly. So by looking at the group numbers, we can determine what are the what is each atom's number. And then the periods in the periodic table tell you the number of shells that the atom has. Now, how about the octet rule? What does the octet rule mean? What do we mean by the octet rule? Judy, do you want to try this one?
Like I don't remember, but like I remember it had to do with the Lewis structure.
Yes, it has to do with the Lewis structure. Yeah, go on. Your memory is so far good. So octet, the word oct means, when you're talking about octagons and octopus, octet means having to do with the number 8. So how about you, Sasan? Any ideas about the octet rule?
Maybe like the chemical bondings and like the valence electrons and stuff of that.
Stuff like that, yeah. So more specifically, if you guys recall, the octet rule was the rule that described when you had bonding in Lewis structure, and described that each atom likes to have a full valence electron shell that has 8, and that is called the octet rule. So looking at this periodic table, for example, so all these atoms except for hydrogen and helium only have 2. They don't follow the octet rule, but all the other ones, for example, this very last column here, these 8, this column 8 here, this group 8, these are all, can you guys tell me, what do we call this last column here on the periodic table? What type of elements are these? There's a special name for them. Anybody know what do we call this last group on the periodic table? They are the
noble gas, but
exactly. The answer is actually right here. These are the noble gases. And what does it mean that they're noble gases? What does that tell us?
with the I forgot what exactly it was, but I remember kind of like
That's okay.
this small part of the gas, like which is not like the oxygen, and like it's like a really different. I kind of forgot about it.
Yeah, so the noble gases are very unreactive. and they are unreactive because they have their 8 valence electrons. They don't need any more. They don't need to gain any more to have 8. They don't need to donate any electrons to reach 8. They have 8. They have 8 electrons in their valence shell. That means they're set. They're happy. They don't want to react with nobody to become more stable and to have a stable octet. Whereas, for example, elements in this column, this group 7 here, fluorine, chlorine, bromine, those have got only 7 electrons in their valence shell. So they need 1 more to reach 8. So they are happy to make bonds with other atoms that are able to give them an electron, to share an electron. Or in some cases, in the case of like sodium and chloride, see, for example, sodium at this end, it's in group 1. So that means it has 1 electron in its valence shell. And in chlorine, it has 7. So with these two, because they have such big differences in their electronegativity, and so this needs 1 electron to become stable. This has got 1 too many electrons to be stable. So these two exchange. Sodium will donate its electron to chloride and says, here, take my 1 valence electron from my outer shell, because by giving it to chloride, then now sodium falls back down into having 8 valence electrons. And so it becomes sodium plus ion. And then chloride has now accepted the electron from sodium. So now sodium becomes Na plus and chloride becomes Cl minus. But by having this extra electron, now chloride has got 8 electrons in its outer shell. So now they're happy. Now they are in this ionic bond. Now you have sodium chloride. They both have achieved a stable octet by forming this ionic bond. But then you also have things like molecules like hydrogen and chloride. So hydrogen and chloride, the difference is not big enough. That electronegativity difference is not big enough to get them to have a complete a donation and acceptance like the way it is with sodium and chloride. So they decide to instead share electrons. And by sharing electrons and overlapping their electron orbitals, now chlorine has got a stable 8, hydrogen has got a stable 2, and they've formed a covalent bond, which is a sharing of electrons. So back to our question of what is the octet? The octet is basically the most stable electron valence that atoms like to have. They like to have 8. So, and then which leads us right into number 5 we talked about, is why do elements make positive ions are on the left side of the periodic table, and those that make negative ions why are they on the right side of the periodic table? Do you guys, can you guys take a chance on answering that? Do you know what the answer is?
Because the left side are metals?
Yeah, because, well, the left side of the table, yeah, they're mostly metals and they tend to lose electrons to become more stable. Whereas on the right side, they are non-metals and they want to gain electrons to have the octet and become more stable and become more like the noble gases here. So yeah, exactly. So it all just has to do with how many electrons they have in their valence shell. The number of electrons these have in their valence shell determines their chemical reactivity and their behavior. Next question. What was the next question? What is the common name for group 18? We touched on that. Group 18, group 8, what are they? They are the noble gases. We talked about that. Noble gases or inert gases, some people call them. And why do these elements usually don't form ions and typically don't participate in any bonds with other atoms? It's
because they have a full outer shell.
they have a full octet shell. Yes, following the octet rule, they are set. They have a full outer electron shell. They don't need to participate in any bonds. Okay, so then we have our table, and we are asked about group 1, 2, or 13. Another name for 13 is 13A. Another name for 16 was 16A. So then we have group 1. What do we call group 1? Group 1 are the
Other non-metal.
So group 1, they're the nonmetals or the alkali metals. Okay. Right here, you can see this is referred to as they're nonmetals, and also they are the alkali metals. So this one is a nonmetal, but the rest of the nonmetals are here. So these are called alkali metals. Group 2 are called the alkaline earth metals here. All right. And then group 3 and 16, they don't have any special names associated with them. How about group 17 here, group 7A here? What are they called? They are called
Halogens.
Yes, they're called the halogens, exactly. They're the halogens. Then we talk about the charge ions of this group. So what are the charges associated with these groups? So on this group, they have how many valence electrons?
1.
1. So if they want to become more like the inert gases here, like the noble gases here, they either need to gain 7 electrons or they need to lose that 1 electron so that they can drop down to the next shell, which does have a stable 8. It's far easier to just lose that 1 electron than to gain 7. So these will typically lose that 1 electron from their outer shell. And by losing that electron, what sort of a charge do you think they develop when they lose that 1 electron?
Positive.
Yes, so the charge on group 1, when they lose that electron, what sort of an ion charge do they have? They have a charge of +1. Now, using that same line of reasoning, we can look at group 2. Group 2, they have 2 valence electrons. And again, it's far easier to drop these 2 than to gain 6. So they will tend to drop these 2 to become more stable, to become more like the noble gases. And what happens when they drop 2 electrons, when they lose 2 electrons, what kind of an ion charge will they have then? These group 2.
+2.
+2, excellent, okay. So now let's take our attention to this side of the periodic table. These last, this last column, let's look at 13, 16, and 17. Okay, so 13, 16, and 17, okay? So group 13 has got how many valence electrons?
3.
3, exactly. So, so by having these 3 valence electrons, and so how about group 15?
5.
And 16?
6.
And 17?
7.
Exactly. So say group 17. Group 17, how many, what sort of an ion charge do you think it will tend to form, and why?
A -1 because it already has 7, so it's really easier to just take one.
So yeah, so as soon as it takes one, it's got one too many extra charges of electron, it has got one negative extra, so it has a charge of -1. And by that same reasoning, 16 will have a charge of,
-2.
yeah, so oxygen, sulfur, selenium. So how about nitrogen? This row here.
-3.
-3, right. So then when you look mostly at these electrons, then they don't very readily form ions. They mostly share electrons and participate in covalent bonds. You don't really encounter an ion of carbon. But what does carbon form, if you recall our in our whole unit, it forms bonds. It forms long carbon-carbon chains, forms covalent bonds with other carbons, and forms very long alkane chains. It can potentially form extremely long alkane chains. So yeah, those are the properties there where that's concerned. Now, let's see what else. Okay, so then we had that periodic table scavenger hunt. So so let's see, where am I sharing? Where am I sharing? Okay. All right, so which one of these elements, can everybody see that periodic table now?
Yeah.
Okay, so which one of these elements is a metal according to the periodic table? So is it a barium, or is it antimony? Which one is it? So let's look at our periodic table. Oh, I'm just going to have to share. I'm just going to share this whole screen with you, because as I'm switching back and forth, it's just too much. There we go. Okay.
Is it Ba?
Right. So it would be Ba. It would be barium. Okay. So then the next question was, question 2, which period is calcium 20 in? So let's look at our periodic table and find calcium 20, and then you can tell me which period it's in.
Four.
So calcium 20 is right here, and it is in period 4. Yes. Next question. What is the number of the group for nitrogen 7? So which group is nitrogen in? So we have our periodic table, and nitrogen is in group
15.
15.
15 or 5A, telling us it has how many valence electrons?
5.
5. Excellent. So which element is an alkali metal? Is it rubidium number 37 or aluminum number 13? So let's have a look. So rubidium number 37, where is that? Right here. Or is it aluminum number 13? Right here.
What was the other one? What was it? I forgot the name.
It was the rubidium
Yeah,
number
rubidium.
37, right? Yeah, so you
Yep.
can tell by the color coding here, it's an alkali metal, and also it's under group 1. Group 1 are the alkali metals. Okay. Then which element is a halogen? Is it sodium number 11 or chlorine 17? Let's have a look. So here it is, chlorine 17 or sodium 11. Which one is a halogen? Again, our periodic table is fully labeled, very easy for you guys to see.
Chlorine.
Chlorine, exactly.
Chlorine.
Chlorine is a halogen. And we always know that the ones right before the noble gases, so here are the noble gases, and the group right before the noble gases are the halogens. So fluorine, chlorine, bromine, iodine, those are all the halogens. Okay. So which element is a noble gas? Is it a neon, number 10, bromine, 35, or oxygen, 8? So let's have a look at our periodic table. Neon number 10, bromine number 35, or oxygen number 8?
Neon.
Neon number 10, exactly. It's in the very last group, last column. These are the noble gases. These are very unreactive. And how many electron dots should arsenic 33 have? Let's see. Arsenic 33. So let's find it. Boom, there it is. So how many electron dots should this one have when you're doing a Lewis electron dot diagram? Any ideas?
5.
5, exactly, just like nitrogen would, just like phosphorus would. And which element has 5 valence electrons? Is it boron number 5 or is it phosphorus 15? Let's have a look. 5 valence electrons. Is it?
I think phosphorus.
It's exactly phosphorus because it's under group 5A or 15. Which element has 18 electrons when it is an ion with a -1 charge? So let's think about when it's an ion with a -1 charge and it has 18 electrons in that state. So if it has 18 electrons when it has a -1 charge, that means normally when it's just an element and it's not an ion, how many electrons should it have then?
7.
It would have 17. So 18 minus the 1, 17 electrons, right?
Yes.
So then let's see which element would have 17 electrons. Which element would have 17 electrons? I'm not talking about valence shell, I'm just talking 17 electrons.
Chlorine.
This element would be chlorine. Yes, exactly. Perfect. Okay. And what atomic number would an isotope of uranium-92 have? So we're talking atomic number of an isotope of uranium-92. So let's take a look at the periodic table. Where is uranium-92? Uranium-92, it's down here in the actinoid series. Uranium-92. What sort of an atomic number should an isotope of uranium-92 have? Any thoughts? Well, let's think back to what does it mean when we talked about isotopes.
Is it 92 itself?
Exactly, it's 92 itself, because 92 is the atomic number for uranium-92. That means it has 92 protons in its nucleus. And an isotope of uranium-92 will also have 92 protons, but it will have a different number of neutrons, making it an isotope. So whatever is the number of neutrons for uranium-92, I don't know right now because I don't have the atomic mass for uranium-92. I need to know the atomic mass of uranium-92, and they don't have it on this table. But by subtracting those two numbers, that will tell me how many neutrons it has. Now, an isotope of uranium-92 will have a different atomic mass, meaning that it will have a different number of neutrons than this uranium-92. So yeah, it would have the same atomic number. Exactly. Thank you for that. And how many neutrons does bromine-80 have? How many neutrons does bromine-80 have? Let's have a look. Where is bromine-80? Where is bromine? So there's bromine-35. So bromine-80 would have how many neutrons?
35.
So you would have to subtract 35 from
45?
Exactly, it would have 45, yeah. Okay, so what else? Do we have more here? Oh yeah, there it is, okay. So then we have this word list here, and we had this exercise here where we were matching these to what is here, okay? And so let's see. So Dmitry Mendeleev developed a chart-like arrangement of the elements called the periodic table, right? That chart-like arrangement, it's this periodic table. This periodic table was developed by a scientist called Dmitry Mendeleev. Some people call it the Mendeleev periodic table. And he stated that if the elements were listed in the order of increasing blank, their properties repeated in a regular manner. And he called this the blank of the elements. Okay, so he stated that if the elements were listed in the order of increasing, so on the periodic table, the elements are listed in the order of increasing what?
Their charge? Or...
So they are listed in the order of increasing atomic number, right? The number of protons,
yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. So here, listed in the order of increasing atomic number, and their properties repeated in regular manner. And he called this the periodic law of the elements. Okay. So the arrangement used today differs from that of Mendeleev so actually, today they are arranged in the order of increasing atomic number. He originally, that's right, originally he had them in the order of increasing atomic mass, but now they're arranged in the order of increasing atomic number. And each horizontal row of the element is called we talked about this, it's called a
Group.
family.
Oh, the horizontal side.
The horizontal, yeah. And each vertical column is called
That's group.
That's the group, yeah. Or because of the resemblance between the elements in the same column, it's called there's another name here for it. There, it's called a family.
Yeah.
So rows 4 through 7, there is a wide central section containing elements, each of which is called so here is rows 4 through 7, and there is this wide section of elements, and these are called the, look at the purple label here, these are the
Transition metals.
exactly, thank you, transition metals. And where were we? Called the transition metals. Rows 6 and 7 also contain 2 other sets of elements that are listed below the main chart, and these are called the blank and the blank respectively. Rows 6 and 7 listed below the chart. So let's have a look. Here we go. Row 6 and 7 listed below the chart, and these are known as the lanthanoid series, and the row 7 is
series.
actinoid series, exactly. And what else? Each of the elements these are that respectively, and then each of the elements to the left of the staircase line of the chart is classified as a blank, and to the right of the staircase line is classified as a blank. So let's have a look at our periodic table. And do you see this staircase line here? So to the right, these are called the
non-metals.
Non-metals. And to the left, these are the metals. Yeah, metals and non-metals. And this is that staircase line sort of separating them. Each of the elements between these 2 main types having some properties like one type and other properties like the other type is called an these are called the, it's called the, yes, they're called the metalloids here. And finally, where were we? Each of the elements in the columns labeled 1A or 1 is called the alkali metals. We already discussed that. And in column 2A or 2, they're called the alkaline earth metals. And each of the elements in column 17 or 7A is called the halogens. And in 18 or 8A, they're called the noble gas. So yeah, that was this area here and this area here. Okay, so we finished Did we finish? Yeah, we finished the periodic table, and I think I covered everything here. Okay, perfect. So let's go back to our Unit 2 review and see if we... So when we were talking about, for example, carbon having 4 electrons in its valence shell, just so to refresh your mind, here is carbon. The number for carbon, the atomic number for carbon is number 6. So that tells us that it has 6 protons. But because we know this is a neutral element, all of these elements on this table are neutral. They don't have a charge. They're not ionized. So if it has 6 protons, it must also have 6 electrons. And so if we look at the rule for how to fill in the shells from before, remember it was 2 followed by 8. So here is 6 electrons. 2 of them go into the first shell, and that's all the number of shells, electrons that this can take. Remember, this is the 1s shell. And then the first shell, the n is equal to 1. And then in the n is equal to 2, you get 8. So here, the next 4 go in here in this outer shell. So that means carbon has got 4 electrons in its outer shell, which is the information we can get from it here being in group 14 or 4A. So when we draw the Lewis structure for a carbon atom, we only show the 4 valence electrons. And that tells us that it has room for 4 more to obtain a stable octet according to the octet rule. And that's why we see carbon able to make 4 bonds, either with hydrogens or other carbons, but it can make a total of 4 bonds. Here it has got 2 double bonds with another carbon, and then a single bond with this carbon and a single bond with this hydrogen. So here we have the saturated and unsaturated. And in this case, when we were talking about isomers of elements of the atoms, but there's also within molecules, there can be structural isomers. And in molecules, when we're talking about structural isomers, it means that they have the same number and same type of atoms. So 4 carbons and 4 carbons and 8 hydrogens and 8 hydrogens, but that they are arranged in a unique way between the two. The two are structurally different. So they're structural isomers. They have, the structure is different, but they have the same molecular formula, C4H8. Both of these are C4H8, but one is a 1-butene, one is a 2-butene. So how about just we talk about maybe some of these support questions. Do you guys want to try any of these? Any of these seem like things you might want to try? So these I should have marked for you very soon and return them to you. And then you have the next set of support questions coming up. So we talked about all of these different types of reactions, the addition reactions. And so maybe I can take some time and we can go through this lesson 8, polymers, which was your independent study unit. So I don't know if any of you have had a chance to look at the material for this lesson yet. Judy, Sasan, have you guys looked at lesson 8 on polymers yet? I did share it with you. Okay, so since we have time in this review session, I might as well talk about it with you guys. It's very short. I think altogether it's like 7 or 8 slides that we can go through together. So in our previous lesson, lesson number 7, we learned about the different types of organic reactions that form many of the organic compounds. And here we can talk about another type of important reaction, polymerization reactions. And polymerization makes many both natural and synthetic polymers that we will discuss here and discuss some of their practical applications. So polymers, many organic molecules like plastics and many of the very important molecules in our body are made up of polymers. These polymers are very long molecules and they are formed by linking, joining together of many smaller molecules, smaller subunits of these polymers. And these smaller molecules are called monomers. So monomers means mono means one. So the single unit is called the monomer. And when you join many of these monomers together, you get polymers. So many polymers are made up of just one type of monomer, but you can also have polymers that are made up of a combination of 2 or more different monomers. Now, you can have natural polymers that occur inside us, like in DNA is a type of polymer, proteins, and complex carbohydrates such as glycogen and cellulose and starch. These are all natural polymers that occur within us, but there's also synthetic polymers. And some examples of these synthetic polymers are things like polyethylenes, which are usually what you find in plastics when a lot of plastics have got the designation PE on them, polyethylene, that's one type of plastics. Lots of adhesives and glues, rubbers, styrofoams, these are all made out of synthetic polymers. And oftentimes the manufacturing of these synthetic polymers is quite dangerous as many of the reactants are carcinogenic. They cause, they're cancer-causing agents. And some of the products that they produce are also highly quite toxic. And then I guess in some cases, the usefulness of many of these polymers is that they're quite durable and long lasting, but on the downside, because of that, they don't seem to degrade in the environment. So we have to be really careful about how much of these synthetic polymers we produce because they tend to have a lasting effect on our environment. They take a long time to go away. They don't break down very easily. So one of the reactions that leads to the formation of polymers is this addition polymerization. So monomers that have double bonds within them, for example, such as this molecule of ethene, has a double bond and it can be joined together in a long chain as a polymer through this addition reaction. So the double bond is broken, and instead it's linked to another CH2. So you can get a very long chain of CH2s, just CH2, 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 CH2. You can have a long polymer of CH2s, for example, a very long hydrocarbon polymer. You can also have condensation polymerizations. And in condensation polymerization, these monomers are joined together by the formation of esters or amide bonds. Here, each monomer has to have two functional groups, one at each end of the molecule. And when you form an ester or an amide, often it's a condensation reaction where a water molecule is lost. And polymers that contain amide bonds are nylons or polyamides, and polymers that contain ester bonds are called polyesters. So these are two familiar types of polymers, plastics that you guys have heard of, nylons and polyester, and these are formed through this reaction. So here, for example, the two functional groups in this monomer are the two hydroxy groups, the two OH groups here, and they form together with another molecule that has a similar functional group. And you can see you can lose the OH and the H from each end to produce a water, and that forms an ester bond right there. So, but what you have to remember that these are some synthetic examples of polymers, but also polymers, whether it be synthetic in the form of plastics, nylons, polyesters, styrofoam, or they can also be natural polymers such as cellulose. Cellulose is the fibrous part of vegetables and part of our food, or whether it be other polymers such as DNA or even rubber that occurs from the rubber tree. These are all natural polymers, and they're really a part of our everyday life. So it's very important that we know something about their chemistry and how they're formed. Particularly important and relevant to us are the natural polymers, proteins. Now, proteins are made up of these polymers, which we call proteins, are made out of monomers, which we call amino acids. And proteins are found in meat and milk, eggs, legumes, beans, also in wool and silk and leather and bone. These are all have protein content. And this protein polymer is made by the condensation reaction between amino acids. So here we have two amino acids, or three amino acids actually. So here is one. So at one end, there is this NH3 group here. And at this end is the COO minus. And when you get this condensation reaction between this amine and this carboxylic acid group, you get condensation of water. A molecule of water is removed, as is highlighted here. And you get the formation of a peptide bond or an amide bond. This is the new bond that is formed now between this carbon and this nitrogen. One molecule of water is lost, and you get this amide bond or peptide bond. And this is how a protein chain gets formed, is through this condensation reaction, through this loss of water and the formation of a series of amino acids joined together by amide bonds. So here on this side of the slide, I just have an example of the different amino acids that exist. There are 20 amino acids in all in nature, and each of them has got the same basic base. So there is a carbon group attached to a hydrogen, and then there's one carboxylic acid group, a COO minus, and on one end there's an amine group as NH3 plus. And then finally, what makes each of these, so this is what's common between all amino acids. As you can see, all of these amino acids have got that same base. And then what they have differently, and that's what makes each one of them be a different amino acid, is they have this different R group, what is called. So this R group is different for each amino acid, and depending on what it is, that's a different type of amino acids. For example, these 3 amino acids up here, these are called the aromatic. They have aromatic R groups. And by aromatic R groups, I mean they have that benzene group, that phenyl group here. And so, so for example, this one is called a phenylalanine. This one's a tyrosine. This one's a tryptophan. And then there's the positively charged R groups. This one is called a lysine. It has a positive NH3 at this end of the R group. This one is called an arginine. This is a histidine, and so on and so forth. So they're based on the different characteristics of these R groups on these amino acids. Each of them has got a different character. Some of them are positively charged. Some of them are aromatic groups. Some of them are uncharged, polar uncharged. Some of them are non-polar, but aliphatic R groups. So very hydrophobic. As you can see, they're just made out of hydrogens and carbons. So these groups tend to be very hydrophobic. They don't like to be in water. They would much rather be in oil and in fat and associated together rather than interacting with any of these things that have water content or water associated with them. And then you can have negatively charged R groups. So as you can imagine, these side chains then also play a role in how different parts of these polymers, these protein, these long chains of amino acid are going to interact with each other. And that gives the character to what ultimately proteins do in our body is they have structural roles. They're what makes up enzymes, and they have to do they form a certain structure that dictates the function of that protein or enzyme in our body. Now, once you have the amino acids joined up together, so here, for example, remember I was telling you that each one of these amino acids have got different names, different characteristics. And then each one of them, for example, this phenylalanine is given a sort of a short form name for phenylalanine. It's a PHE for phenylalanine. For tyrosine, it's TYR. For valine, it's VAL. So here, when you have these all linked up together, so here you have one amino acid with whatever is its R group here, it could be any one of these things. Here's another one with another R group and a third amino acid with a different R group. So then you get a string of amino acids all joined up together, like valine, histidine, threonine, asparagine, glycine, phenylalanine, glutamate, glutamine, alanine, arginine, all of these things just join up together like strings on a bead. But these strings on a bead arrange themselves in dense globular structures, which we call proteins. And protein shape and function depends on this sequence, this primary sequence of amino acids. So the primary sequence is just simply the order of the amino acids in the sequence. This is the primary sequence of a protein structure. It's just which amino acid follows which other one in a chain. So this primary structure then forms what's called a secondary structure. So these chains of amino acids then start to arrange themselves in what are called secondary structures. So they either form themselves into an alpha helical coil, or they form themselves into what are called beta sheet structures. So an alpha helical coil, as you can see, the amino acids kind of start spiraling around each other. And if you remember from our lesson about hydrogen bonds, it's the hydrogen bond that stabilizes this, this arrangement, this secondary structure. The secondary structure of these polypeptides is then determined by this hydrogen bonding between this oxygen atom of the carbonyl group and the hydrogen of the amino group attached to this nitrogen of another amino acid. And the same on beta pleated sheets. You have these chains and they run in opposite directions and they form this hydrogen bond across each other, and that's how they become stabilized and they form these sheets instead of these helices. And these two types of structures, beta pleated sheets and alpha helices, are known as secondary structures. So the secondary structure is how does this segment of this peptide orient itself into some sort of a secondary regular pattern. And from there, then that leads to tertiary structure and quaternary structure. Tertiary structure is how the protein molecule then coils overall into some three-dimensional shape. So you have some sort of a packing of these alpha sheets and some alpha helical coils and these beta pleated sheets, and there's even some loops and some more flexible parts that attach them together, and they all kind of pack together to form a three-dimensional structure. And sometimes you have these, which are just a single unit. Some of these may then form, you have multiple of these subunits coming together to form a quaternary structure. It's how these different protein molecules come together to form a larger aggregate structure here. So this is one example that is very important in nature, is the formation of proteins and how proteins are really just a polymer of amino acids. And I just wanted to tell you the story of proteins and the different level of structure of proteins and how you can have the primary structure. The primary structure then dictates what type of secondary structure they form. So the sequence of the amino acids that follow each other tends to determine whether they will go into a coil or whether they will form these pleated sheets. It all depends on what sort of a hydrogen bonding pattern they can form and how these R groups, what sort of a space they occupy and how they're going to pack in together. For example, these beta pleated sheets, they might have shorter R groups, as you can see. They cannot have big bulky R groups. So the amino acids that have smaller R groups, such as serines and threonines, tend to, and glycines and alanines will tend to pack themselves more typically into these beta pleated sheets where there isn't really too much space in between to pack these big groups. Whereas some of the other groups might be more suited to this arrangement of a helical and an alpha helix coil here. And then each one of these R groups has got its own type of chemistry, its own type of property, which then allows whatever is this final protein that is made up of here to bind other proteins, to bind other substrates, to catalyze reactions, to bind metals, to form, for example, in hemoglobin, that's a protein. It might have the right type of atoms arranged in a way to then be able to bind iron and be hemoglobin. Hemoglobin is very important protein in the transport of oxygen in the blood. So proteins are a natural polymer that is very important, and proteins are made out of the polymerization of these amino acids that lead then to longer protein chains that form bigger three-dimensional structures. Another class of natural polymers are carbohydrates. Carbohydrates, as many of you know, are found in breads, in pastas, and potatoes, fruits. They are the sugars and starches. They serve as the primary sources of energy for us in cellular respirations, and also form the structural material for many plants and organisms. Many molecules of glucose, so here we have a single molecule of glucose, and you can link many of these glucose molecules together to form a large polymer that will then act as a good storage molecule for storage of energy. All of a sudden you have, instead of single molecules of glucose just flying around and being quickly metabolized, they tend to form these large either glycogen or starch or cellulose, where then they become storage molecules for energy. For example, in animal cells, you can have glycogen, which is a branched polymer of glucose that is a good form of stored energy. You can have starch in plants, and this is usually a mixture of linear and branched forms of glucose as well. You can have cellulose, and cellulose is a component of cell walls that is primarily makes up wood. And although we humans, we can't digest cellulose, it does provide dietary fiber to us, but lots of animals such as horses and cows, they can eat cellulose. They can digest that fibrous part of that you find in hay and in alfalfa, and they can use that as a source of energy. So, so the cellulose parts of the plants grown to produce human food for us are frequently used also as animal food. So glycogen, starch, and cellulose are another class of polymers, the carbohydrates, the polysaccharides of glucose. These are all three are polymers of glucose, as you can see the single units in here. And the way they are different from each other is that in the type of bond and the degree of branching, just how much branching takes place here, and how big they get, how big of a molecular mass they have. And these polysaccharides are defined as a large polymer that consists of many monosaccharides such as glucose. And finally, we have lipids. Lipids are also a type of polymer. Lipids, and by lipids, I mean fats and oils. They are large ester molecules. And lipids, these fats and oils, provide long-term storage of energy in both animal and plant cells. And they also can act, can have a structural role in cell membrane and in the protection of major organs. They can also play a role as regulatory hormones, and they can also be vitamins. And these fats and oils, these large ester molecules, are soluble in nonpolar solvents, such as benzene and hexane. And you should probably know why they would be soluble in nonpolar solvents. That's because they have these typically long fatty acid tails. And these fatty acid tails are very hydrophobic. They don't have any oxygens, or they don't have anything that would be happy making hydrogen bonds in water. So this part of this major part of this molecule just doesn't like, is not hydrophobic, would be much happier in nonpolar solvents such as benzenes and hexanes. So fats contain glycerol, the molecule glycerol, and this part of this molecule is glycerol, that is bonded to 3 long chains of carboxylic acid. So here it's the carboxylic acid end, the COO. And oils have the same structure of fats, but they're liquid at room temperature. And that just has to do with whether these fatty acid tails are saturated or if they're unsaturated, and the number of singles or double bonds that they have. And finally, waxes. Waxes are esters of these long chain alcohols and carboxylic acids. So this molecule of triglyceride here that I've shown here is one of these very typical fats that we have circulating through us. So, and it has this alcohol component, which is the glycerol, and the glycerol is a 3-carbon alcohol molecule, so 1, 2, and 3 carbons, and it also has 3 hydroxy groups. So this O, and then an H. There would be H's here, but once it reacts together with this carboxylic acid chain, it loses the OH from the carboxylic acid and the H from the glycerol, and it's a condensation reaction. You can imagine a molecule of water leaving here. So when glycerol has its hydroxy group, it can bond very well. It can make hydrogen bonds with water, but it can also form bonds with these 3 fatty acids and form in a condensation reaction to form this large polymer, this lipid, which we call a triglyceride. And this long chain carboxylic acid here, as you can see, it has got a very long hydrocarbon chain. And then at this end is the carboxylic acid, so CO, and then here would have been another OH, which was then removed in the condensation reaction. And this portion of it is the fatty acid tail. That's how a typical polymer of triglyceride looks, and that's how it would be formed from the alcohol and the carboxylic acid and the condensation, the removal of water, and these bonds being formed, this ester bonds. And support question for you guys to practice with. And then the key questions for this independent study unit, this one you're supposed to read up on and research a little bit more on your own time. If you choose to do it, it's a bonus question. You don't have to do it, but if you do it, then it can go towards improving your mark and dropping other marks, other assignments that you got lower marks on. So if you do choose to hand it in, you have to hand this in by this Sunday, together with key question number 7. You should also hand in number 8 if you choose to do it. This is a bonus. All right, any questions about polymers, polymerization?
No question.
All right, all of that was pretty simple, pretty straightforward. So yeah, if any of you choose to do this, it's this question. You have to create a brochure about polymers. So basically just design it on an 8.5 by 11 inch piece of paper. And it's worth 30 marks. And these are the key points that I'm looking for and how much marks they are each worth. Okay. So you can do this kind of a design on Word. You can do it on PowerPoint. You can do it on Illustrator. Whatever is the software that you like, you can create this on that. And in previous years, I've had some very nice brochures on polymers that were handed in with a lot of good information on them. All right, so back to our review. So here's another slide from our previous lesson. And here we talked in great detail about glycogen. And as you heard in today's lesson, glycogen is a polymer. And this is formed again by the condensation reaction, where hydroxide and hydrogen are removed between two sugar molecules, two glucose molecules, and you get long chains formed by this glycosidic bond. And sometimes there's branching that takes place, and you get a big polymer of glycogen. So that's the condensation reaction. And also, as we talked about again in today, the condensation reaction in proteins, same way. So these are those two amino acids that we talked about. All can have their own unique R group. It makes them different from each other. And then when you get this condensation reaction, this removal of H2O, you get the formation of a peptide bond. So any questions?
No question.
No questions from you, Sasan. How about you, Judy? How are you feeling?
No,
So at this,
I'm
yeah.
good.
What's that?
No questions.
No question. Okay. So at this point now we've, guys, we've finished units 1 and 2. So unit 1 had to do with atomic theory and talked about the different models of the atom and what is our current understanding of the atom and the arrangement of electrons around the atom. And from that, we learned about all the different orbitals and the electronic structure. We learned about how you can have the overlap of orbitals that take place when a bond is formed between two atoms, and how through a process of hybridization, you get a bond formed, whether it's a single bond or a double bond. And what does it mean if it's a sigma bond versus a pi bond? What are the characteristics of that? Then in our second unit right now, we went to talk about organic chemistry, and we talked about hydrocarbons, and we talked about their functional groups and their reactivities. We talked about naming conventions and how to draw the structures based on the name given, and how to give the name based on the structure that's shown. So all of these things, we talked about fractional distillation, we talked about cracking. So we have covered quite a lot of ground, and I really hope that you guys have been following through with trying these support questions. I can't stress enough just how useful it is for you to try these support questions. And if you have questions and if you don't understand, to then bring them up with me. So we have one more unit to cover that will start next week. And that unit is so our unit that we will be starting next week is thermochemistry. So we are going to be covering thermochemistry. And at the end of unit 3, which covers rates of reaction, that's when we are going to have our midterm exam, which will cover material from all 3 of these units. So I really urge you to start preparing and start thinking about what it is that you feel you understand fully, what it is that you feel like you need to get more time on, because we have time between now and the midterm to go over these concepts and to clarify and iron out any questions or any confusions anything that's unclear. So we have time at the end of the lessons, we have time before the lessons, and we have time in one more end of the unit review. And at the end of the review for Unit 3, I can answer questions about Unit 1, Unit 2, and Unit 3. And I really hope that you guys have some questions for me and you feel confident and that you've studied enough and tried enough of these questions that you feel like you're going to do well on the midterm. I really want everybody, well, right now it's just 2 of you, but I especially want the 2 of you to do really well on your midterm. So please, whatever you feel like you don't understand, you want me to review, go through with you again, don't be shy. Please don't hesitate to reach out to me. I'm happy to review lessons with you, talk about concepts, things that are confusing, things you didn't understand, things that I didn't explain properly the first time around. I'm happy to go through again and again. If it takes a second time, a third time, whatever it is. So come prepared with questions. Okay. If we don't have any more questions for tonight, we can call it a night. If you guys want, I can stay on longer with you and go through any questions, anything you want to work on or answer. It's up to you guys.
I have no question.
You have no questions. Great, Sasan. How about you, Judy?
I'm good.
You're good. Okay, so we can finish this class now, and maybe you guys can use this remaining half hour that you normally would have been receiving a lesson to try out some questions or to work some more on some of your key questions that you're supposed to be handing in this Sunday. Okay, then in that case, I wish you all a good night. Okay, have a good evening.
Have a great
Thank
night.
you. You too.
Okay,
Thank you.
take care. Bye-bye.
Bye.
Goodbye.